So based on the electrical conducting properties of the materials, we know the materials are classified into three types. I told you in the beginning, electrostatics. Do you remember, Swarna?
Yes, sir.
Even in the current electricity also, in the beginning I told you. So based on the parameter called electrical resistance, the materials are classified into three types. They are conductors, insulators, semiconductors. The materials which are readily accessible for electrical conduction, they are called electrical conductors. The materials which don't allow electricity, conduction of electricity, uh, they put messages now. Hmm? Sir, I'm feeling dizzy today. Yeah, students are like that. What can we do, Swarna? After you become doctor, you should find some medicine, right?
Yes, yes, sir.
Hmm. Okay. So, based on the electrical conducting properties, based on a parameter called resistance, the materials are classified into three types: conductors, insulators, semiconductors. Conductors are those which allow the electricity to pass through. Insulators will never, of course, in their existing state, and those other materials whose conducting properties will be lying in between those of conductors and insulators, they are called as conductors. So as far as conductors are concerned, conductors, they have high electrical conductivity. Resistance is relatively low, the electrical conductivity is moderate, and their alpha, I told you, ohmic and non-ohmic conductors. Do you remember? After the formula, RT is equal to R0 into 1 plus alpha T for ohmic conductors, and for the semiconductors, RT is equal to R0 into 1 minus alpha T. So the temperature coefficient of conductors is positive, means their resistance will increase with the rising temperature. Whereas insulators, as it is in their physical state, they don't allow the electric current to pass through. Even I gave the examples, and there is a possibility for them to have decreasing resistance with the increase in temperature. So their high resistivity is very very low, means it's understood conductivity and resistivity, they are of opposite nature. So conductivity will be very very low. Semiconductors, their electrical properties will be lying in between those of conductors and insulators. So examples: germanium, silicon for semiconductors. Conductors all the metals. Mercury is a wonderful conductor of heat. Human body, salty water, water with salts, added salts, and a few drops of acid will work like wonderful conductor of electricity. And insulators, rubber, plastic, mica, bakelite, they're all called insulators. And as far as semiconductors are concerned, yeah, the resistivity is higher than conductors and less than uh, insulators. Plus, at 0 Kelvin, they don't conduct. They behave like insulators only, and their electrical conductivity can be increased by two methods. One, at room temperature, enough number of electrons will be available in the crystal lattice because of the breakage of covalent bonds. And other way, adding some impurities. Addition of impurities will disturb the energy levels and energy gapping. Yeah, I'll share my. Just I wanted to give some introduction and go further. Right? So uh, this is by either by increase of temperature. Just room temperature is enough to break the covalent bonds. Otherwise, add some impurities at any state, irrespective of temperature. If you add some impurities, then we'll have the good electrical conductivity. So this is how we can increase the electrical conductivity in semiconductors. All group 4 elements will come under semiconductors, but germanium and silicon, mostly they exhibit good electrical conductive properties. And the pioneer in this field who spoke elaborately about it. And the very important, striking invention he did was the Shockley. He designed the first ever transistor in August 12, 1912. Sorry, in August 1912, the first ever transistor was designed, fabricated, which totally changed the face of electricity. Before that, the all the items were bulky in size. Now we got thumb top computers, laptop computers, even wristwatch. Our wristwatch, a small strip, is acting like a computer. That's all because of the extensive research happening in the field of the semiconductor devices. So this is all about the classification of the three materials based on their electrical conductivity. Now we'll see the other aspects. I'll try to show you some slides. Yeah, these are the energy levels in solids, especially for isolated atoms. The energy levels will be like this: 1s, 2s. Please note it down, Swarna.
Yes, sir.
Yeah. So 1s, 2s, 2p, 3s, 3d, and so on. They continue. Just for a single atom it is, but atoms will never be single. In solids, all the atoms are closely packed. Yes, so atoms are closely packed, and this is I am discussing for an isolated atom with the energy states 1s, 2s, 2p, 3s. S orbital can accommodate 2 electrons, p orbital can accommodate how many? Telma.
Eight. Eight, sir.
Huh?
Eight.
No, s orbital can accommodate 2, p orbital can accommodate 6.
Eight.
6. 3 subshells, 2 electrons in each subshell, so 6. D orbital can accommodate 10. Sir, no? Forgot.
Yes, sir.
Am I right or wrong?
Yes, sir.
Yeah, this is filling of electrons, of course, is strictly in accordance with the Pauli's exclusion principle. So there will be large number of orbitals in the isolated atoms like this: 1s, 2s, 2p, 3s, 3d, 4s, 4p, 4d, 4f, and so on. Yes or no? So these are all the different energy levels present in an isolated atom. Then, in case of these atoms, whenever are two or more than atoms are approaching each other, inner shells are not disturbed. Inner shells means you can say 1s, 2s, 2p. But other shells, 3s, 3p, 3d, and so on, what happens is, because of the covalent bonding between the atoms of these solids, the outer energy levels will be shared among all the atoms, forming a well defined band of energy. So that band of energy thus formed is only called as energy band. What do you call that? Yes, ma'am. That is called as
Energy
energy
band.
band. So this is how you can see here. 1s is ground level. This is 2s. Observed interatomic distance is shown on the x-axis. Corresponding energy is shown on the y-axis. So this is how the energy levels of the outer orbits taking part in the covalent bond are overlapping, means they are overlapping or interacting with each other to form a well defined bands of energies. So in this also the electrons are not free in the crystal lattice, even though energy bands are formed because of the interactions among the atoms, especially for the electron with the electrons present in the outer shells. Because of the interactions among the atoms, the energy levels of these interacting atoms will be shared among themselves, forming a band of well defined energy. So this band of well defined energy, thus formed out of interaction among the atoms taking part in the covalent bonding, is called energy band. What do you call that? Yeah, Swarna.
Energy band.
And please write the definition now. The closely spaced energy levels, the closely spaced energy levels into which a discrete energy level splits into which a discrete energy level splits into due to due to the atomic interactions of the solid, due to the atomic interactions of the solid, is called is called the energy band, is called the energy band. Next, if the yes completed, Swarna.
Yes, sir.
Yeah. Suppose if the energy band is corresponding to electrons which are in covalent bonding with the neighboring atoms, then that is called as valence band. And if this energy band is corresponding to the electrons which are accessible for electrical conduction, then that is called as conduction band. There will be, of course, some difference of energies between this valence and conduction bands. Valence band will be of lower energy, conduction band will be of higher energy. So the difference of energies between these two bands is called energy gap or forbidden gap. What do you call that? Energy gap or forbidden gap. So based on this energy gap, we now categorize the materials into three types. What are they? Conductors, insulators, semiconductors. So let us say the three different types of materials classification done based on the energy gap between the valence and conduction bands. See, this is the case of insulator. Insulator have completely filled valence bond is there, and almost empty conduction band is there. Completely filled valence band, completely empty conduction band will be there. The energy gap is nothing but, I told you, valence band is of lower energy, conduction band is of higher energy. The difference of energies between the valence and conduction bands, we call it as forbidden energy gap. So in case of insulators, the forbidden energy gap is greater than 6 electron volts. Means under any circumstances, very important point, under any circumstances, you cannot supply that much high energy to the electron in valence band to cross this forbidden gap and enter into the conduction band. That is highly impossible. I repeat once again, it is impossible to supply energy present in the valence band of an insulator to cross the forbidden energy gap with more than 6 electron volts of energy and enter into the conduction band, and thus electrical conduction insulators as it is in insulators without changing its physical state is not possible, so they don't conduct. Coming to the conductors, you can see clearly. So valence band, conduction band, they are overlapping. This shaded portion, see, Swarna, are you able to identify, ma? Sai, are you able to see?
No, sir.
You're not seeing?
No,
No,
sir.
sir.
Why, ma?
Sir, only that black screen only, the computer only coming, sir.
From the beginning, I've been showing different slides. You're not telling? Huh? Wait. Already I did 3 slides, right? Hmm? Okay, I'll try to show it on whiteboard. We'll do one thing. You should tell. I'm. I thought you are seeing. That's why I'm moving forward. Hmm? You're able to see the whiteboard?
Yes, sir.
Yes, sir.
Okay. Yeah, are you able to see the diagram on the whiteboard? Are you able to see, ma?
Yes,
Swarna?
sir.
Yes, sir.
Yeah, this is what I started with isolated atoms. So isolated atoms will have the energy levels 1s, 2s, 2p, 3s, 3p, 3d, and so on. You said 2s to p level will have 8 electrons. Do you remember? Swarna? Swarna?
Yes, sir.
Yeah, tell me, respond, right? I'm doubting whether you are able to see the whiteboard or not. Are you able to see the diagram on the whiteboard?
Yes, sir.
So here, s orbital will locate 2 electrons. This is how you'll be showing, applying the Pauli's exclusion principle. Do you remember? Opposite spins, correct? P orbital, there will be 3 subshells. And there is a rule also how these subshells are filled. Then D, there will be 5 subshells. Anti-clockwise spin is positive, clockwise spin is negative. So this is how the different energy states are present in the isolated atoms. So if the free electrons are there in the outermost shells, the electrons, the materials will be considered as conductors. If no free electrons are there, then insulators. At 0 Kelvin, if they are not conducting, and with the increase in temperature, they are conducting, means semiconductors. Next, I told you about the interacting atoms. So this is a diagram showing how the energy levels of atoms will be interacting. Are you able to see? Sai,
Yes, sir.
you're seeing on the
See,
board,
sir.
whiteboard.
Ah,
Yeah. So whenever in solids, all the atoms are closely packed. So atoms cannot exist independently in solids. So because of the interactions taking place in the among the atoms, the energies corresponding to the outer shells of these atoms taking part in the covalent bond will be interacting to form a well defined band of energies called energy band. Here only I told you to take down the definition of energy band as the closely spaced energy levels into which a discrete energy level splits into due to the interactions among the atoms of the solid is only called as the energy band. There only I said if the energy band corresponds to the valence electrons, we called it as the valence band, and if the energy band is corresponding to the electrons which are accessible for electrical conduction, we call it as conduction band, and the difference of energies between them is called as the energy gap or forbidden gap. Means the electron should be either present in valence band or they should be present in conduction band. Energy gap cannot accommodate any electrons, but if you want any electrons present in the conduction band, valence band, to enter into conduction band, minimum energy should be given. This is the overlapping of orbital energy levels and formation of the different energy bands. Then next I have discussed about we discussed valence and conduction bands. So valence band represents the range of energies processed of the valence electrons of all the atoms in a solid. They will be either completely filled or incompletely filled. This is the highest filled energy band, and electrons in this band are not accessible for electrical conduction. So we should be having clarity that valence band electrons are not accessible for the electrical conduction. This is a very, very important point. Next, we call it as CB. CB means conduction band. So this band is of higher energy. It may be either empty or partially filled. So if it is empty, insulators, even semiconductors at 0 Kelvin, they have empty conduction band, completely filled valence band, empty conduction band. Whereas in case of conductors, yes, electrons are present in the conduction band. So, and the difference of energies between these two bands, we call it as energy gap. So that is called as energy gap. Based on this energy gap, now we are trying to categorize the materials into three different types. This is the first one. Yeah. Are you able to see conduction valence band? For insulator, I am first explaining. This is the valence band, completely filled. Conduction band, totally empty. And there is a forbidden energy gap of more than 6 electron volts. So without disturbing the physical state of the insulator, like mica, uh, bakelite, rubber, even dry air, distilled water, they are all insulators, they don't conduct. Without disturbing the physical state, you cannot give that much very high energy, 6 electron volts for electron valence band is very, very high energy. So that much energy cannot be supplied to the electrons present in the valence band, enabling them to cross this energy gap. See the movement of cursor. Electrons are completely filled in this valence band. By somehow or other, you attempt to give energy. So it's impossible for these electrons to cross this energy gap and enter into the conduction band. That's highly impossible. Therefore, electrical conduction as such in the uh, insulators is not possible. Whereas coming to this conductors like copper, aluminium, silver, gold, platinum, chromium, nickel, they're all good conductors, all metals, all metals. Mercury is a liquid metal. Water with added salts means the water that we drink contains salts. So it is a good conductor of electricity. And if you add few drops of acid, then it becomes a conductor of electricity. Even in inverter batteries, Swarna, they add this distilled water. It's not distilled water. They add few drops of acid, sulfuric acid. They add. So, with added impurities or salts or acids, water also becomes conductor. Pure water is a insulator. So this is the valence band. This is the conduction band. So valence and conduction bands are overlapping. Means electrons are loosely bound to the parent atoms in conductors. Whenever any electric field is applied, we discussed about drift speed. Do you remember? Swarna. Swarna, do
Yes,
you
sir.
remember drift speed?
Yes, sir.
So here the drift speed is given by NEAVD expression. The electric current in any conductor will be given by N, number of free electrons present in unit volume of the conductor, E, electronic charge, A, cross-sectional area, VD, drift speed. So once we apply electric field, the electrons which are loosely bound to the parent atoms and will be randomly moving inside the conductor will acquire drift speed, and this much current is constituted by them, whose formula is NEAVD. So this is about the conductors. Okay. Then coming to the insulators. Yeah, this is about the sorry. Insulators and conductors we finished. This is about the semiconductors. Just look at this. Now this is the situation at 0 Kelvin. Situation of the conductor at 0 Kelvin. 0 Kelvin means what is the temperature? Minus 273.15 degrees centigrade. So at 0 Kelvin, the valence band is completely filled. Swarna, are you
Yes,
seeing?
sir. Yes,
The
sir.
valence band is completely filled. Conduction band. Do you have any electrons in the conduction band? This each dot, what is shown here, will represent an electron. Okay, so this is the valence band. It's shown here. This is the conduction band. Energy gap will be maximum up to 1.5 electron volts. Easy will be less than or equal to 1.5 electron volts. In insulators, energy gap is greater than 6 electron volts. Conductors, no energy gap. Whereas in semiconductors, there is an energy gap of 1.5 electron volts, less than or equal to. Maximum is 1.5. So, but germanium and silicon, it is less than 1 electron volt. So, this is about the semiconductors contains completely filled valence band with all the electrons, S2P6 configuration, 1s2, 2s2, 2p6. all shells are completely filled. No electron is free in the crystal lattice. Suppose if it is 2p5, yes, one electron is free in the p orbital. That can take part in electrical conduction, but semiconductors no. 1s2, 2s2, 2p6, s2p6 configuration, s2p6. So in semiconductors, the configuration is s2p6. So s2p6 means s orbital can accommodate maximum of 2 electrons, p orbital can accommodate maximum of 6 electrons. Therefore, all the orbitals are completely filled. No free electrons are available in the crystal lattice. Hence, electrical conduction is not at all possible at 0 Kelvin, that is minus 273.15 degrees centigrade. But once if you can give some energy to this semiconductor, just bring it to the new room temperature, bring it to the room temperature, then that takes care of uh, the electrons present in them. According to, we have Boltzmann law. What is that? Kinetic energy kb, even we referred it in dual nature, 3 by 2 kt. The kinetic energy gained by any particle once the temperature becomes capital T is given by 3 by 2 kb into T. This kb is called Boltzmann constant. This kb, universal gas constant by Avogadro number. So some 1 point something into 10 to the power of 23 minus 23 will have. Joule mole inverse will be the unit. So this is called Boltzmann constant. And if you can raise the temperature, you need not specially increase the temperature of semiconductors. Just what you need to do is keep it to the room temperature. Room temperature means how much? Around 300 Kelvin. 23 degrees, 27 degrees, like that room temperature. So it will be equivalent to 300 Kelvin. So 0 Kelvin to room temperature means 300 Kelvin. Yeah, this is enough for these electrons to cross the forbidden gap, enter into conduction band, and take part in the electrical conduction. So in semiconductors, just the room temperature will support the electrical conduction. This is about the semiconductors. You can note down the some more examples. Germanium and silicon are elemental semiconductors. Please note down. Germanium and silicon are the basic semiconductors. So we are categorizing the materials into three types: conductors, no energy gap; insulators, energy gap with more than 6 electron volts; third one, semiconductors. So maximum energy gap will be less than or equal to 1.5 electron volts. So basic semiconductors are germanium and silicon. Chemically made conductors. So these are elements directly from the periodic table. Some compounds made chemically in the laboratory are also, they function like semiconductors. In this, we have inorganic, organic materials. As far as inorganic, cadmium sulfide, gallium arsenic, cadmium selenium, etc. Organics, of course, I can't even pronounce their names because chemistry, somehow it won't go into my mind. Anthracene. Can you give me chemical formula of it? Anthracene. and this is Phthalocyanine. Phthalocyanine. pH is silent there. THALO. CYANIN. So phthalocyanine. pH is silent there. Of course, it should be doped properly. But mostly we'll prefer these pure germanium and silicon with the compounds of germanium and silicon other than all these things. They also exhibit semiconducting properties, but we don't prefer. Now, this germanium and silicon in pure form, we call it as intrinsic semiconductors. What do you call them? Germanium and silicon in pure form are called intrinsic semiconductors. These are all compounds, means mixtures of more than one, two, or three substances. Therefore, we prefer mostly pure germanium and silicon, and next preference is this inorganic. Organic normally we don't prefer because of various reasons. The reasons like energy gap. Energy gap, if it is nearly 1.5 also, we don't prefer. Energy gap, we see that ensure that even though all materials up to 1.5 electron volts will be considered as semiconductors, but we put a limit to maximum less than or equal to 1 electron volts. That is possible only in germanium and silicon and these inorganic semiconducting compounds. Organic semiconducting compounds will have energy gap more than 1 electron volt. So we don't prefer them. So this is about the classification of materials based on, yes, the energy gap. Now, we'll be classifying the semiconductors into two types. One is pure or it is also called intrinsic semiconductor. Next one is impure or extrinsic semiconductors. Pure or impure intrinsic semiconductors means the germanium or silicon, and impure or extrinsic semiconductors means the pure semiconductor plus selected impurities. How these impurities are selected, that we will discuss next. So this is classification of semiconductors into pure or intrinsic semiconductors. Yeah, Swarna, are you there?
Yes, sir.
Okay. So pure or intrinsic semiconductors, germanium and silicon. Impure or extrinsic semiconductors means we add some selected impurities from the periodic table to increase their conducting properties. I told you at 0 Kelvin semiconductors won't conduct electricity. By raising the temperature, this is the relation I gave you, ohmic, non-ohmic conductors. Resistance at any temperature for semiconductors, because they are non-ohmic, is given by the formula, yes, RT is equal to R naught into 1 minus alpha T. Means as the temperature increases, resistance will be decreasing. So they are non-ohmic. So these non-ohmic conductors, they don't obey Ohm's law, and will be able to get conducting properties either by rise of temperature or addition of impurities. Instead of rising temperature, we prefer the second option, that is selected impurities. This process of addition of impurities to a pure semiconductor, we call it as doping. Whenever any athletes will go to Olympics, other games, now I think Japan Olympics are going on. Other day, our Prime Minister was complimenting all those participants of Japan Olympics. So they first do this doping test. What for? Because they will be taking steroids into their body. So with the added steroids in their bodies, they get more stamina, and they will be getting medals. So after this doping test has become so popular, many gold medalists, they have withdrawn the medals. They have banned them permanently from participating in these international or national athletic competitions. Even in cricket also, now this doping has become a big problem. So international cricketers, they accepted that yes, we took minor levels of doping. Doping means they took some injections. So the pure blood is added with some impurities. What for? To increase their abilities, to increase their performance. So doping medically means adding some impurities to the pure blood. Here, as far as technology is concerned, selected impurities will be added to pure semiconductor. That process is called as doping. Now we'll see what are these intrinsic and extrinsic semiconductors. Have you noted this?
Yes, sir.
Okay. Sai, you're there?
Yes, sir.
Be a sincere man. If you attempt to throw the blame on faculty, you never shine in your life. Understand?
Okay, sir.
You should be honest for your sake. Not, don't try to attempt to cheat your parents or your uncle Madhusudan sir or me. And in that attempt of cheating, you are trying to throw the mud on a honest man. That's not at all good. I don't like such people. So try to have some honesty and sincerity. You are just in the pursuit of knowledge. You are a student. Being a student, you should be more honest to achieve success. If Brahmin says lies, no life for him. Remember.
Okay, sir.
Yeah. Then yes. So let us talk about this pure or intrinsic semiconductors. This is P type. Yes, this one. Yeah, this is a pure germanium or silicon. Similar situation will be there. There'll be, I told you, S2P6 configuration. So no electron is free in the crystal lattice. Because it's two-dimensional, we could show only 4 electrons. One will be above, other will be below also. Yes or no? So this is a pure semiconducting crystal. So all the do you find any free electron in the crystal lattice? This is the situation at 0 Kelvin. Is there any free electron in the crystal lattice? I want to answer. Swarna, you're not responding, right?
Sir,
Are there any free electrons in the crystal lattice? I asked.
no, sir.
Are you able to see the diagram there?
Yes, sir. Free
Yeah.
electrons are there, sir.
Free electrons are there,
No, sir. No, sir. All are bonded, sir.
all are bonded. So in the crystal lattice, at what temperature? Uh,
At 0 degree Kelvin, sir.
you should not say 0 degree Kelvin. It should be only 0 Kelvin. Understand?
Yes, sir.
So at 0 Kelvin, no no free electrons are there in the crystal lattice. All the electrons are in covalent bonding only. Yes or no? What do you say? So is the conduction possible in this?
No, sir.
Because no free electrons are there in the crystal lattice, no electrical conduction will take place. Now, if it is so, with the rise in temperature, say the temperature increased to room temperature T degree centigrade. Room temperature in Thoryur, I think maybe 30 ma.
Yes, sir.
So 30 degrees, or I will put 27. Round figure we will get. So this will be equal to 300 Kelvin. At this temperature, these electrons present in the valence band, they gain energy. I'll yes, same diagram in terms of covalent bonds is now shown in terms of uh, energy levels. Yes or no? So this is valence band, and here is conduction band. This is at 0 Kelvin, and this is temperatures greater than 0 Kelvin. Are you able to see? Say yes or no, Ray?
Yes, sir.
Yes, sir.
Yeah. So at 0 Kelvin, once again I am showing, earlier we have shown in the covalent bonds, now we are showing in energy bands. So the the valence band is completely filled with electrons, and the conduction band is completely empty. The forbidden energy gap with more than 6 electron volts is there. So as it is at 0 Kelvin, no electron can cross this energy level and enter into the conduction band. So again, this is valence band, this is conduction band. I said the temperature is 27 degrees centigrade, means this will be equal to 300 Kelvin, let us suppose. So from 0 Kelvin to temperature increased to 300 Kelvin. What is happening? See, some electrons crossed this energy gap and they entered into conduction band. Are you able to observe them? All these red dots in conduction band are the migrated electrons from where? From valence band. Yes, here is a uh, vacancy of electron is there. So the electron from here is jumped there. Similarly, the electron from valence band had gone there, and the electron from here came here. Similarly, the electron here has come there, and then this electron might have gone there. The electron which is supposed to be present in the valence band might have gone there. So what is similarly this electron might have gone here, means now I think you got the clarity. all the electrons present in the valence band, some of them got some energy. I gave you the formula. What is that? The kinetic energy gained by these electrons is given by 3 by 2 kb into T. What is this kb means? Boltzmann constant. Capital T, absolute temperature. So the electrons present in the valence band will gain energy with the rise of temperature. Normally only, you're not heating it on, keeping it on a frying pan. Just you kept it in room temperature. That is enough for them to cross this energy gap and enter into the conduction band. You can note down these things. Three, we are doing intrinsic semiconductors. Please note it down. Have you done, ma? Swarna,
Sir.
have you finished?
Yes, sir.
Okay. You should note all these values, and you should also show how these electrons are migrating from valence band to conduction band. So, with the rise of temperature, few of the electrons present in the valence band have entered into the conduction band. Once the electrons are there in the conduction band, they are accessible for electrical conduction. That's how the electrical conduction is possible in them. Now, this each atom is losing one electron. This is atom lost one electron. So it gains a positive charge. Do you agree or not? So this is atom lost its electron. So
Yes.
it gains positive charge. This becomes a positive ion. 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 So what is the immediate consequence of sorry, we said with the gain of energy, electrons in valence band have migrated to conduction band. So now electrons are available in the conduction band for electrical conduction. In consequence of that, we have some atoms which lost their electrons in the valence band. Sorry. So these atoms present in these electrons present in the valence band of the atoms, they left the atoms and entered the conduction band. They have become free. Now these atoms will become positive ions. Do you agree? Respond fastly, Ray.
Yes, sir.
So these positive ions of the atoms are only called as holes. What do you call them? Holes. Electrons, negatively charged particles. After gaining energy, some of them will enter into the conduction band. Then holes. They are positive ions of the atoms which lose their electrons. They'll be present in valence band. So once you apply electric field, suppose this is how you applied the electric field. So apply the electric field here. Then what happens? Electrons will be drifting towards which plate? Huh? Electrons with negative charge will be drifting towards which plate? Speak out, ma.
Towards positive plate, sir.
Yeah, towards positive plate. Why you are taking time to respond? Next, these holes present in the valence band, how they move? they move towards negative plate because they are the positive ions of the atoms. So electrons will be attempting to drift towards positive plate, holes will be attempting to drift towards the negative plate. Let us call the drift speed of electrons as VE, and the drift speed of electrons is VD, VE. Please keep noting. The drift speed of electrons is VE, and the drift speed of holes is VH. So now we will get a total current I in semiconductors as the sum of electron current in conduction band and hole current in valence band. So I get the number of electrons in the conduction band will be equal to number of holes in the valence band, because if one atom loses an electron, look here, magnified view. If one atom is losing an electron means that's called positive ion. If one electron appears in conduction band, one hole appears in valence band. Therefore, we can say the number of holes will be equal to the number of electrons. So Ne will be equal to NH, and therefore I get charge on hole plus E, charge on electron minus E. So amount of charge formed on electron and hole also will be equal. Cross-sectional area will be same. Only difference will be drift speeds of electron and hole. Therefore here V and VH, drift speeds of electrons in conduction band and holes in valence band. So if electrons are shifting towards positive plate, holes, electrons in conduction band, they will be shifting towards uh, positive plate, and holes in valence band will be shifting towards the negative plate when electric field is applied. Thus, a current is constituted given by total current I is equal to NEA into VE plus VH. Very important formula. You will be getting problems based on this. So the total current in the semiconductors, in conductors, see the difference. In conductors, the current is only because of electrons, and the formula is NEAVD. This is in conductors. Whereas in semiconductors, the total current is the sum of electron current and hole current. So it is NEA into VE plus VH. So this is about the semiconductors. Have you noted down? Noted, ma?
Yes, sir.
Yeah, this formula is important. You can expect some problems based on this. Shall I clear the screen?
Okay, sir.
Okay. Then we have this P-type and the N-type extrinsic semiconductors. So before that, let us see the relative comparison between the three materials. Some conceptual questions may come based on them. You can have a look. I'll try to share it in my YouTube channel. If you want, you can refer once. Right, ma? Swarna?
Sir.
Yeah. So this is serial number, conductor, semiconductor, insulators. What all points we discussed so far are summarized in this table. So conductors, valence band and conduction band overlap each other I've shown the diagrams also. Semiconductors, valence band and conduction bands are separated by a energy gap less than or equal to 1.5 electron volts. Whereas in insulators, the valence and conduction bands are separated by energy gap of 6 electron volts. Forbidden energy gap is 0, maximum 1 electron volt, here 6 electron volts. At room temperature, they are readily accessible for electrical conduction with high conductivity, whereas semiconductors at room temperature, the conductivity will be moderate. At 0 Kelvin, they don't conduct. At room temperature, they conduct. And at room temperature also, their conduction is not nil. They don't conduct. Conduction is not there. Similarly, the resistivity values are given. Numerical values of resistivity are given. It's a comparative table showing the different properties of the three important materials: conductors, semiconductors, and insulators. So this is the range of resistivity and conductivity of conductors will be 10 to the power of 2 to 10 to the power of 8 Simon meter inverse will be the conductivity of conductors. 10 to the power of 5 to 10 to the power of minus 6 Simon meter inverse for semiconductors. Very low, very high resistivity, 10 to the power of 11 to 10 to the power of 19 ohm meters, very high resistivity and very low conductivity. Next, valence and conduction bands overlap. I've shown you diagrams very clearly for clarity. And germanium and silicon, valence band is almost full, conduction band is almost empty, of course at 0 Kelvin. At room temperature, yes, I've shown how the electrons are migrating and electrons and holes are formed. Valence band is completely filled, conduction band is completely empty. So all metals, germanium, silicon, rubber. We can show even the formula for current here. This is current is given by NEA VD. VD is the drift velocity of drift speed of electrons. Only electrical conduction is only by electrons. That point also can add. Here, by electrons in valence band and holes in conduction band. Electrons in conduction band, holes in valence band, conduction. And the electric current formula is given by the formula NEA into VE plus VH. Here, because there is no electric current, no need of writing that formula. So this is a comparison table. I added that electric current is only by electrons in conductors. Electric current is by electrons in conduction band and holes in valence band. Even I wrote the formula for electric currents. So once again, I'll show you those diagrams. Yeah, this is insulators with energy gap of more than 6 electron volts. This is conductors, no energy gap. Valence and conduction bands are overlapping. Electrical conduction is only by electrons. Next, whatever I have shown earlier, I am showing again because this table is there with us. And then here is the this is semiconductors. At 0 Kelvin, valence band is completely full, conduction band is completely empty, energy gap will be less than 1 electron volt for germanium and silicon. And this is what we have shown for semiconductors. Then we are talking about the intrinsic semiconductors. Pure or intrinsic semiconductors also we discussed. So this is the diagram we have shown just now. Now we are classifying the substances into intrinsic semiconductors, and I have explained you. Now we have to talk about the impure or extrinsic semiconductors. This is 3, 2. Impure or extrinsic semiconductors. So we have two possibilities in this. One is pure semiconductor plus a pentavalent impurity like phosphorus, arsenic. Next, pure semiconductor, please note down, plus a trivalent impurity like indium boron. So this semiconductor formed with the added pentavalent impurity is called N-type extrinsic semiconductor. Simply N-type semiconductor. And this pure semiconductor with added trivalent impurity is called P-type semiconductor. So we have two types of semiconductors. One is N-type semiconductor, other is P-type semiconductor. If you add a pentavalent impurity like phosphorus, arsenic, etc., then we will get a P-type extrinsic semiconductor. And if you add a trivalent impurity if you add phosphorus or arsenic, a pentavalent impurity, you will be getting a N-type semiconductor. If you add a trivalent impurity, indium or boron, then you will be getting a trivalent impurity. You will be getting a P-type. I repeat once again, pure semiconductor, with chemical terms, they don't go into my mind. So pure semiconductor with a pentavalent impurity like phosphorus, arsenic will give us N-type extrinsic semiconductor. Pure semiconductor with a trivalent impurity like indium boron will give us a P-type semiconductor. So today we will learn these two types of semiconductors and conclude our class. Yes. Have you noted down, ma? Swarna?
Yes, sir. Yes,
Oh,
sir.
okay. Yes. Now, see this crystal structure of germanium. In this, what are we doing? A trivalent impurity atom, boron, is added. Have you observed? Have you observed, ma?
Yes, sir.
Yes. So, boron valence is 3, means this is 1 electron. This is the second electron. This is the third electron. So, the 3 electrons of valence electrons of boron present in the outer shell of the boron atom will form covalent bonds with these 3 germanium atoms. Correct? Yes or no? Speak out, Ray.
Yes, sir.
Now, so one bond is empty, correct or not? This
Yes,
fourth
sir.
bond is empty, but any empty bond cannot exist. So what will happen is Yes, it snatches one electron from the neighboring covalent bonds from anywhere. So this electron will come and settle here. Thereby, this germanium becomes an ion, correct? One atom of germanium is snatched by this boron. One electron of germanium, one valence electron of germanium is snatched by this boron atom for stabilizing or consolidating its position inside the crystal of germanium. So thus germanium atom has now become a positive ion. This positive ion thus formed because of the addition of one impurity atom boron is called as hole. So one hole is formed. The positive ion of, it's shown here, arrow mark is wrongly shown. So once you add a trivalent atom, it snatches one electron from the neighboring germanium atoms. Thus germanium atom will become a positive ion, means it becomes a hole. So hole is created in the valence band of germanium with the addition of this trivalent impurity boron. Understood? Correct or not? Speak out, man.
Yes, sir.
So, under the action of electric field, these holes, hole is any ion is unstable. What happens? This hole picks out electron from the neighboring germanium atom. So, like this. Again, this germanium atom will become hole. Next, another germanium atom will be here. So, one electron is taken from the neighboring germanium atom. Here it becomes hole. Means, suppose if you apply an electric field like this, negative positive, because we are showing drifting in right direction. So we are finding that the hole is shifting towards right, correct? Now can you add one electron? Is it possible? Can you add one boron atom? Is it possible? Answer to my question. Can you add one boron atom practically?
No, sir.
No. Let us assume that you added 1 microgram of boron. So it contains, microgram means 10 to the power of minus 6. 1 gram atom contains Avogadro number of atoms. So finally 6 into 10 to the power of 17 impurity atoms are present in 1 microgram of boron. So if you, for one impurity atom, with the addition of one impurity atom, you are getting one hole. When you are adding 1 microgram of boron, how many holes are formed? Yeah, please tell. How many holes are formed? How many holes are formed? Are you not able to see? Sai,
6 into 10 to
6
the
into
power
10
of
to the
7.
power of 17.
17. Speak fastly, Ray. Where is the energy? So, morning, lots of energy should be reflected in your speaking. You see how I'm speaking? The thrust must come from the body and mind. So, if you add just 1 microgram of impurity boron, it contains 6 into 10 to the power of 17 atoms. So, each boron atom is resulting in the formation of one hole. So how many boron atoms are added here? Assuming that 1 microgram of boron is added, 6 into 10 to the power of 17 boron atoms will be present in 1 microgram. So how many holes are created in the crystal lattice? 6 into 10 to the power of 17 holes, and they constitute hole current. So these holes, once they start drifting towards the negative plate in the applied electric field, then they constitute the hole current. Simple. So thus, in p-type extrinsic semiconductors, the holes are the majority charge carriers. In p-type, why the name has come like this? In p-type extrinsic semiconductors, the majority charge carriers are holes. Majority charge carriers are holes. Holes carry positive charge, hence they are called as p-type. P-type means p-type semiconductor means the majority charge carriers in these extrinsic semiconductors are the positive ions of the atom, hence they are called as p-type extrinsic semiconductors. Simple. No much explanation is needed for this. I repeat once again, when a trivalent impurity is added to the boron, when a trivalent impurity is added to the boron, to stabilize its position, consolidate its position, here I have shown very clearly. So it was snatching the electron. This is how I have shown how the electrons are snatched from the neighboring germanium atoms. Electron is snatched and it formed a consolidated covalent bond with the neighboring germanium atom, leaving positive ion of germanium. So that is called hole. Then this germanium atom will pull one electron from the neighboring. Thus, the holes will start drifting in a direction opposite to the electric field towards the negative plate, thus constitute a hole current. So because even if you add 1 microgram of boron to the pure germanium atom, will have 6 into 10 to the power of 17 holes will be formed. So these will be acting like the charge carriers. Because they carry positive charge, this extrinsic semiconductor thus formed with the addition of the trivalent impurity like indium or boron, because the majority charge carriers are positive ions, hence it is called as p-type extrinsic semiconductor. Okay, understood, ma? So this is the diagram.
Yes, sir.
Yes. Now this is the forbidden gap, and this is after addition of the boron impurity. Yes, large number of holes when compared with few electrons in the valence conduction band. The number of holes present in the conduction band are more. Therefore, the electrical current is because of holes in valence band. Since holes carry positive charge, hence these semiconductors are called as p-type semiconductors. And here because here the impurity atom is accepting electrons for the covalent bond formation, hence we call this impurity as acceptor impurity. The impurity that is added to the pure semiconductor is called the acceptor impurity. This acceptor impurity energy level will be shifting towards the valence band. Hence, under no circumstances, electrons in valence band can cross, because the gap between the reference energy level, we call the reference energy level, which is the center of gravity of valence and conduction bands, as Fermi level. What is this Fermi level? So it can be considered as the center of gravity for valence and conduction bands. So if in any electron, if it is able to cross this Fermi level, then automatically it can enter the conduction band. So because of the addition of this impurity, trivalent impurity, the Fermi level will be shifting in downward direction very close to valence band, increasing the gap to the conduction band. Therefore, electrons can never cross this energy gap and enter into the conduction band in p-type semiconductors. So only possibility, the majority charge carriers, majority charge, there will be few electrons in conduction band, minor, they are called as minority charge carriers. The majority charge carriers are holes in valence band which carry positive charge. Hence, they are called as p-type extrinsic semiconductors. So, three important points are there. Number one, when trivalent impurity is added to pure semiconductor, the trivalent impurity atom will try to form covalent bond by snatching electrons from the neighboring germanium, thus creating a hole in the valence band. And thus, if at all you can imagine that you have added 1 microgram of impurity, almost 6 into 10 to the power of 17 holes will be available in the crystal lattice of germanium. Under the action of electric field, these holes will drift towards negative plate, constitute hole current. That current is called hole current. So since holes are the majority charge carriers which carry positive charge, hence this is called as p-type extrinsic semiconductor. Second point, the reference energy level, which can be considered as the center of gravity of valence and conduction bands, is called the Fermi level. If electron in valence band is able to cross this Fermi level, then you can take it for granted that it enters into conduction band. But here, because of the addition of this trivalent impurity, this Fermi level will shift towards the valence band, decreasing the chances for the electrons to enter into the conduction band. Third, this impurity, which is accepting electrons from the pure semiconductor for the formation of covalent bond, is called acceptor impurity, and that energy level of Fermi level is called acceptor energy level, which is shifting towards the valence band and lies very close to the valence band. So these are the three important points for this p-type extrinsic semiconductors. Now we'll also do for n-type extrinsic semiconductors. I'm clearing this. Then the next one is n-type extrinsic semiconductor. No. I thought it's waste of drawing many diagrams. That's why I prefer this style of doing. Only theoretical, no much mathematical formulae are there. Yes. Now is this diagram clear, ma? Swarna?
Yes, sir.
Yes. So this is a pure germanium crystal. Now here one impurity, pentavalent impurity, arsenic is added. Clearly shown there, pentavalent impurity atom. So see, this is first electron, second electron, third electron, fourth electron. How many valence electrons are there? Valence electrons in arsenic. How many? 5. Correct? Pentavalent means what? 5 valence electrons. Speak out, Ray. Swarna,
Sir,
how many electrons are there in arsenic?
5 valence electrons, sir.
Yeah, that's why it's called pentavalent. So out of 5 valence electrons, 4 valence electrons will form covalent bonding with the 4 germanium atoms. 1 valence electron is left free. So by the addition of this pentavalent impurity, 1 electron will be free and is accessible in the conduction band. So this impurity donates electron to the semiconductor. Hence, this impurity is called donor impurity. What do you call? Donor impurity. I repeat once again. When you add a pentavalent impurity arsenic to the pure semiconductor, out of 5 valence electrons, 4 valence electrons, I put the numbers also there. 4 valence electrons will form covalent bond with the neighboring germanium or silicon atoms, The fifth electron left free will be accessible in the conduction band and readily take part in the electrical conduction. As said, even if you add 1 microgram of arsenic, there will be 6 into 10 to the power of 17 electrons will be available. That is almost equivalent to 0.9 amperes of current, very large current. 900 milliamperes of current will be available just by the addition of arsenic. So thus, this impurity, because it is donating electrons for the electrical conduction, hence we call it as the donor impurity. Yeah, we can show the same like this. Yes. See, N-type semiconductor. Large number of electrons are found in this. See, these are all the electrons. How these electrons are available? Because of the pentavalent impurity, not from the pure semiconductor. So all these electrons are available in the conduction band because of the pentavalent impurity added to the pure semiconductor. So since electrons are the majority charge carriers, hence electrons carry a negative charge, hence it is called N-type semiconductor. Very few holes will be there. So holes are minority charge carriers. Electrons are majority charge carriers. Since electron carry negative charge, hence we call them as N-type extrinsic semiconductor. Now, the Fermi level, as I said, will be shifting nearer to the conduction band, increasing the accessibility for the electrons to enter into the conduction band. Hence, the Fermi level is called donor level because the impurity is donating electrons to the pure semiconductor. Hence, we call that energy level as donor energy level. So with this, we completed the different types of materials based on conducting properties. Then we introduced the concept of energy bands. Then we classified the materials into conductors, insulators, semiconductors based on energy band. Then we have seen semiconductors, classification into pure and impure semiconductors. Then in impure semiconductors or extrinsic semiconductors, we said there are two types of extrinsic semiconductors. One is P type, other is N type. P type, I repeat once again, P type is formed when a trivalent impurity is added to pure semiconductor. So the impurity accepts electron from the pure conducting atoms, hence from the pure semiconductor atoms. Hence it is called acceptor impurity level. Acceptor impurity. The acceptor energy level will lie very close to valence band. So holes are formed in the valence band, and minority charge carriers are electrons. Therefore, the electrical conduction in the P type are measured maximum by holes. Hence, holes carry positive charge. Hence, we call it as P type. Coming to the other one, when a pentavalent impurity is added to the pure semiconductor atoms, the fifth valence electron will be helping in the electrical conduction, increasing more number of free electrons in the conduction band, shifting the donor energy level to the nearer to the conduction band, because this impurity added to the pure semiconductor is donating electrons for the electrical conduction. Hence, we call it as donor impurity. So we got two types of extrinsic semiconductors. Yeah. So we got two types of extrinsic semiconductors. One is P-type and other is N-type extrinsic semiconductors. Using it, we form an interface that's called PN junction, that we'll see in the next class. PN junction, PN diode as a rectifier, and then transistor. With this, I think we'll try to complete in one more class. Purely conceptual. So not instead of wasting time in drawing the diagrams, I preferred standard diagrams from the standard reference books, and I attempted to explain. Swarna, I should still get energy. You are not as energetic as you were. Hmm?
Yes, sir.
Okay. Yeah, become fast. When I ask a question, immediately you should respond. Then I'll be moving little forward with more interest. Sai,
Yes, okay.
be active, be honest, keep working. Nothing is impossible in the world with efforts. Remember,
Yes, sir.
yeah, escapists will never have any chance in this world. Sincere and honest fellows only will go come up. Escapists
Okay,
will always go down. It's a fact. For the time being, you may manage, but long run, sincerity and honesty only will pay you back.
okay, sir.
Yeah, keep that as a fundamental point of your life. Otherwise, no chance. I've come up from a very remote village in Vishakhapatnam district. Till I complete my MSc, we don't have electricity. We got electric power once I started teaching in a government junior college as a physics lecturer. Then only we got TV and all. So, from a remote village, now I have become a project guide of NASA. I've become a resource person to Gulf schools. It won't happen without sincerity and honesty and dedication. Yeah. If you want to continue, be sincere and honest, be regular. Otherwise, tata bye bye. Tomorrow and day after also we have evening sessions for na 11th class. Thermal
Yes, sir.
expansion. Okay, bye. As said, Swarna, you work out all the current electricity from read concepts, what I explained, do previous NEET questions, and just inform me in the evening, right?
Yes,
I'll
sir.
put some problems for you. Okay,
Yes,
I'm
sir.
ending the session. We'll meet in the next class. Bye.
Yes, sir. Thank you, sir.
Okay.